Hi, I'm Gregory Flores, and I'm here to introduce to you the system UCSD has in its structural engineering program called FocusSequences. Let's get started. We'll first go over a general context of what FocusSequences are. Basically, you can think of them like Harry Potter houses. There's 4 different ones students get divided into. There's civil, which I put as Gryffindor because most people go into it. Aerospace, which is Ravenclaw, because I've heard it's hard like aerospace engineering. Geotech, they help, and SHM, which is a lot of research with graphs and coding. Now, unlike Harry Potter houses, SE students are put into these groups after 2 years of already being in the program, and we get to choose for ourselves which ones we go into, which is pretty cool. First, we have civil structures. It specializes in designing buildings and bridges to be really strong so they can withstand disasters, mainly earthquakes, tsunamis, floods, hurricanes, and tornadoes. Some of the careers you can go into through this focus sequence are structural design, making architectural ideas work. They might get questions like, can you make a building look like this? Forensics, they get asked why architectural designs turned out not to work. Non-structural components, they get asked how stairs and other parts that hang off of structures still affect the structure. And research and development, like the professors at UCSD who study earthquakes with our shake table. Now, this is the focus sequence most students go into, and the one I'm thinking of going into. This is mostly because it aligns with my goal, which is ultimately to help the California housing crisis, which is basically homelessness, such as how we still have so many tents in places like downtown. It also seems to be the most versatile and applicable, and from what I hear, it's the easiest thing I can trust myself with the most. To get to that point, I'm thinking of becoming a field engineer because I like the idea of going to the sites to work with teammates. The past me image is me doing my Eagle project. Second, we have aerospace structures. They do the same stuff as civil, but with air-related structures, mostly vehicles. They could be in the air, space, water, or land. Oh, you can think of it in 2 groups, military and civilian. If you go into this focus sequence, you might end up working for the Navy, Air Force, or even NASA. Each strives for aerospace engineers who'd answer questions such as, how can we optimize the design of X vehicles to make it more fast or efficient or safe? Back when my parents were at UCSD, my dad worked for Sally Ride, so there's plenty of opportunity in this focus sequence. If not in the military, you could work for an airline like Boeing or design drones to watch or deliver to people. Next is geotechnical engineering. Besides bathing in dirt, they focus on solving problems between humanity and soil and rocks. They are important whenever you have a component in contact with the ground because they make sure it'll hold. They have many challenges, such as being unable to see through the ground, so they have to guess what's going on in there with limited data. They can sample soil from the ground, but its properties change when removed. Modeling what's going on between soil and water is difficult. Finally, they have to account for different types of soil and property measurements. So the difference between soil and rock is that soil is made up of solid particles, water, and air. Rock is also made up of this, but includes cementation, so all the materials are packed together. Knowing this, along with other extensive knowledge, lets geotechnical engineers answer questions such as, how much will my building settle? Will my building affect others? What if there's an earthquake? Why are you bathing in dirt, etc.? Okay, wait, sure. Last but not least, we have SHM. They focus on detecting damage and determining whether it affects the structure's performance. This damage could be caused by impulse type events like crashes, natural disasters, similar to civil, extreme events like the drought in the picture, or man-made disasters from military or terrorism. Knowing how to do this leads to solutions to questions such as how can I efficiently monitor my airplane every flight? How can I monitor an area that cannot be accessed with a wire? How much will this monitoring system cost, etc. And here we have a case study about the Gumdang Bridge in Korea, which was first built in 2002. UCSD's leader in SHM, Professor Lowe, wanted to know whether they could put a massive sensor network in the bridge. Luckily, their sensors and tests were determined it was possible, which was one of the first successes of structural health monitoring. This is Gregory Flores. Thank you for listening.